Hello, folks. Today in this video, we're going to talk about electrical current and resistance. So, electrical current is a measure of the flow of charge through a conductor over a period of time. If you have a wire, it's a way for us, in a sense, to measure the speed of those charges in that wire, how fast or how much charge gets through a section of that wire in that time. Now, we typically think of our charge conductors being electrons, but electric current can be any type of charge. Now, our equation for current is fairly simple here. We give it the symbol I, and it's just the change in charge, delta Q, divided by the change in time, which is T. Now, typically, our units for current we're going to see are amps or amperes, typically abbreviated with the letter A. And all an amp is simply a coulomb, which is our unit of charge, divided by 1 second. So anytime you're using amps, you want to make sure that the time you're thinking about is in seconds. Now, the direction of electric current is a little strange, and that's because current is defined as the flow of positive charge through a circuit. So when we state the direction of current in a circuit, we are assuming that uses a positive charge. The problem with that is that we know that electrons are typically our flow or our thing that conducts current, and so electrons will flow against the flow of current. And so if you have a circuit set up here, if you take the positive terminal of a battery, current will flow out of the positive terminal this way and then back into the negative terminal. But because electrons are negative, they'll flow the exact opposite way. Electrons will flow from the negative terminal to the positive terminal. This is just a sign convention. It's just a historical thing. So just know that current flows from positive to negative or high to low potential, whereas electrons will flow from low to high potential. They will flow the opposite way. So let's take a look at a few example problems here. First one says, how long will it take a wire to conduct 5.4 coulombs of electricity at a current of 2.5 milliamps? Well, we know our equation is that current is equal to our charge, delta Q, divided by the time, delta T. They give me my current here in milliamps, so 2.5 times 10 to the minus third amps, just replacing milli with 10 to the minus third. And that's got to equal my change in charge, which is 5.4 coulombs divided by the time. Using our algebra tricks, cross, multiply, divide, whatever works best for you, I ended up getting a time of 2.2 times 10 to the third second. The next one's a common type of question. It asks how many electrons will pass through a wire carrying a current of 4.8 into 4.1 amps in 2 minutes. I've got to find the number of electrons. To do that, I probably want to find the amount of charge going through first. So I use I equals delta Q divided by delta T. I know that my current here is 4.1 amps. I know my change in charge is what I want to find. And I know this is 2 minutes, but when I use amps, I have to change that to seconds. 2 minutes is 120 seconds. If I solve that out for my change in charge or how much charge flows through, I get 492 coulombs. Then I have to remember that basically in a coulomb, or sorry, in one electron, you have 1.6 times 10 to the minus 19th coulombs, that elementary charge. So I can simply take that 492 coulombs, use the 1.6 times 10 to the minus 19th coulombs as a conversion factor, and I end up getting, it looks like 3.1 times 10 to the 21st electrons. So quite many electrons there. Now, we can think more about the microscopic level of what's happening in a wire through a few other terms. The first one's called current density. Current density is a measure of the current flowing through a cross-sectional area of a conductor. If I'm thinking about a wire and I'm just thinking about a slice of that wire, it's a way to measure the current just through that little bit of wire. So current density, I give the symbol J, and it has units of amps per meter squared. And it's just the current divided by the cross-sectional area. The nice thing is the direction of this current density is the same as the flow of the current normally. This also leads us to a microscopic term called the drift velocity, the average velocity of electrons through a conductor. If you set up a current along a wire, it will actually cause the electrons to drift through the wire. They don't actually drift at the speed of the current, but they instead have a drift velocity that is proportional to the current. The equation for that, the drift velocity, is the current divided by N, which is the carrier density. That's like how many electrons are in the material that you're dealing with per unit volume. How much like how many electrons there are there. Then we've got the current, of course, the cross-sectional area, and then finally, typically the carrier that we're going to be dealing with is the electron. So we're going to be dealing with the elementary charge as the charge of our substance there. So let's try some examples here. It says, what is the current through a wire with a radius of 0.025 meters and a current density of 1,000 amps per meter squared? Well, I know my current density, J, is equal to the current divided by the cross-sectional area. The only tricky thing with this problem is that they've given me the radius of my wire. Wires, we're going to assume, have a circular cross-sectional area. So we just need to remember when we plug in our numbers here that the area of a cross-sectional, that is a circle, is pi r squared. So to solve for my current, I'm going to plug in pi times the radius, 0.025 meters squared for my A there. And when you solve out for the current, I got a whopping 1.96 amps. Then it asks what's the drift velocity of electrons in a copper wire carrying 50 amps of current, which has a carrier density of 8.5 times 10 to the 28th and a cross-sectional area of 3.31 times 10 to the minus 6th meters squared. So to solve that out, what we want to do is go ahead and set up our drift velocity equation. VD is equal to I over NAE. Plugging in my numbers here, I've got 50 amps of current, which is quite a lot, but it is something you can encounter in your house. Some very large, particularly large appliances are rated up to 50 amps. 8.5 times 10 to the 28th is my carrier density. My cross-sectional area they've fortunately given me, so I don't have to figure that out. I actually looked it up. That's the cross-sectional density, cross-sectional area of typical 12 gauge wire you'd use in your home. And then lastly, the charge of the electron, which is that elementary charge, 1.6 times 10 to the minus 19th coulombs. Just solving that out, I get a relatively low velocity, 1.1 times 10 to the minus third meters per second. That is not very far or fast in a particular second. So charges, electrons, do not flow through wires very quickly. I'm not saying that current doesn't, but the actual individual electrons do not drift very far, very fast. Okay, our last concept is all about this idea of resistance in a circuit. So ohmic materials, those are materials that obey Ohm's law. Ohm's law tells us that the current flow through a conductor is proportional to the applied voltage, the electric potential. So Ohm had figured out that for most materials under a large range of voltages, their current will be proportional to the voltage that you apply. The slope of this relationship, the proportionality constant, is called resistance. It's a measure of the flow or the opposition to the flow of electric current. So Ohm figured out Ohm's law, which is that V equals IR. V is your voltage, measured in volts. I is your current, of course, measured in amps, which we've been dealing with. And then finally, R is resistance, given a term after Ohm called ohms, which is symbolized by the Greek letter omega. Now, resistance can be related to more fundamental things in a circuit. While we're going to be talking about circuits a lot now, it's time to talk about some circuit notation. Here's a handy list of simple circuit symbols. We'll see more things. For example, we've already seen capacitors, which are represented by two parallel lines, whereas batteries or single cells in a battery are represented by different shaped lines. But we're going to see lots of different symbols, and those will come up as we go. But these are kind of the simple ones that'll be used in a lot of our circuits that we're going to see. So two big quick things. If you're talking about circuits, you can measure things in circuits using two devices, a voltmeter and an ammeter. A voltmeter is a device that measures voltage between 2 points in a circuit. So any 2 points in a circuit will have a difference in electric potential between them. If you measure over a battery, you'll find a difference in electric potential between the two sides of the battery. For example, a 12-volt battery, if you put a voltmeter between the two, should read 12-ish volts. But you can do that across anything, across a lamp, across a resistor, anything you can put in a circuit. To measure something with a voltmeter, you have to put it across the thing. So it has to be wired in parallel. An ammeter is actually placed inside the circuit and measures current. And since it needs the electrons to flow through it, you have to put it in series, which means you're putting it in line with all the other objects. So that was a bit about symbols. Like I said, we can take resistance, though, and connect it to the actual fundamental parts of a material. Resistance, it depends on the resistivity of a material. Resistivity and its inverse, conductivity, are properties of a given material that is a measure of its ability to conduct current. So if you have a wire here, that wire is made of some material which has a resistivity, and you can see a table here of some common resistivities of different metals. That wire is going to have some length and some area, and the resistance R, which is measured in ohms, of that material is just simply the resistivity, which is the Greek letter rho, times the length divided by the cross-sectional area. Now, like I said, conductivity and resistivity are inverses, so you can easily convert in between them. If you're given resistivity, just take the inverse and you get the conductivity using that equation. Finally, this brings us back to current density. That current density, J, is actually proportional to the conductivity. I'm just noticing my slides are screwed these up. So go ahead and flip those in your notes there. Resistivity should be rho, and conductivity should be sigma there. Anyway, current density is proportional to the conductivity times the electric field strength between two places. And of course, electric field strength is just measured in volts per meter. Okay, folks, that is it for resistance, current, and conductivity. Thank you guys so much for watching. Have a fantastic rest of your day.